Hello, I'm Antonio Sala, and in this video we are going to model a heating element as a first-order dynamical system, assuming an exponential profile of its internal temperature. In some other materials, we have considered also a first-order model of a heating tank, but assuming that we have a steering element so that it makes all temperatures inside the tank the same, so we can assume that the outlet temperature is equal to the mean temperature. However, in many cases, that's not the case. The other extreme case can be a long pipe, a tubular heat exchanger in which, assuming laminar flow, there is no steering, so changes in inlet temperature travel with some delay to the outlet. Then we are going to study how to approximate this thing via a first-order model, but in general, partial differential equations associated to these long tubular heat exchangers have some exponential in-space solutions in steady state in thermal equilibrium. In the system, we have three inputs: input flow at a given inlet temperature, an external input signal, this inlet temperature, and the heating power. We have some constant parameters. The state variable will be the temperature. Of course, in a partial differential equation model of a long heat exchanger, we'll have a different temperature in each position, but in first-order approximations, we'll assume that our state variable is a sort of mean temperature of the fluid, and we'll define that mean temperature later on. If it's a state variable, it's because our model will consist in writing the equations of its time derivative. In this kind of systems, we need to carry out mass and energy balance. In this case, incompressible fluid, constant volume mass balance is trivial, 1 liter in, 1 liter out. And in the case of energy balance or power balance, as the mass inside the heating tank is constant, the rate of change of the stored energy as heat in the fluid inside the control volume will be mass times specific heat times rate of change of temperature. We are assuming 0 of temperatures, the outside temperature, and 0 of energy, the enthalpy of the fluid at that outside temperature. Of course, assuming that there are no phase changes. If we are heating water, we are not making steam, we are not letting it freeze. So this will be the storage as thermal energy of the fluid. And other things that enter the balance will be this heat transfer, power from the resistor, and minus a certain thermal conduction coefficient times the inlet temperature. So this is heat transfer without mass transfer. And then we have mass transfer, mass entering the control volume, the tank, with a given energy, and mass and exiting the volume with a given energy as well. Now the inlet temperature is fixed, and we have some kilograms per second of mass entering, which is the volumetric flow times density. So that thing multiplied by the specific heat and the inlet temperature will be the rate of change of the energy inside the tank due to this fluid that is coming with non-zero thermal energy. And we will subtract in our balance a similar term rising from the quantity of fluid per unit time times specific heat times outlet temperature. So we end up with this power balance in which we say that what enters minus what exits plus minus the net power from heat transfer must be stored as thermal energy in the liquid that's being heated or cooled depending on the sign of this balance. In this case, capital T will be sort of mean temperature, and the only thing that's left is replacing the outlet temperature by a function of inlet and mean temperature from our steering or internal temperature profile assumptions. For instance, a perfectly stirred tank, the outlet temperature will be equal to the mean temperature inside, or the unique temperature inside, because everything is at the same temperature. So if we make this, and if we take this to the other side, then we get this state equation and output equation. So this will be the model for a perfectly stirred heating tank. If we assume a non-uniform temperature profile, but for instance a linear one, saying that by assumption we think that the mean temperature is the average between inlet and outlet temperature, if we solve for the outlet temperature, we get this expression. Then if we replace that in our previously discussed power balance, we get this, and we have another plus t in here, so we end up with twice this coefficient of the transport term comparing to the perfectly stirred version. And again, dividing both sides by this, we get this state equation and of course this output equation for the linear temperature profile case. Next, we will consider our main goal here. In fact, the above two cases will be particular cases of this one. We will assume that our temperature profile is exponential in length. Of course, if we model as a first-order dynamic system, it will be also exponential in time. But in this case, we will assume an exponential in length distribution. This is x, this is x equal L, x equals 0. We may assume, for instance, if no heating is on, that the inlet temperature, first it gets cooled fast because it has a large temperature difference with the outside, but as temperature differences get smaller, then the rate of power also gets smaller, so we have an exponential temperature profile along this tubular heat exchanger. Indeed, we can write partial differential equations governing the laminar flow long tubular heat exchanger and the steady state solution of that partial differential equation. So when we are in equilibrium and this temperature profile does not change with time, then we can prove that this is the exponential solution for the so-called stationary heat exchanger profile. This is a famous expression in heat exchanger literature. But we as control people, we don't wish to work with partial differential equations because they are infinite dimensional, so we prefer to work with low-order approximations, either for control design or even for simulation. It will be much faster to simulate, let's say, a first-order system than a 400th order system, finite-element partial differential equations. In summary, our goal is preserving this steady-state equilibrium temperature distribution, adding some first-order time dynamics apart from this. Inspired in this, we will assume that our internal temperature distribution is something like this. Indeed, it is in steady state, but our leap of faith will be assuming that it is so as well in the transient state, which is just an approximation, of course. Then, when x is 0, the exponential will be 1, so the inlet temperature will be A plus B, and when we replace the whole length of the pipe, the outlet temperature will be this expression. When we operate this thing, we will know the inlet and outlet temperature, say with thermocouples, but we don't know A and B. However, we have two equations and two unknowns, A and B. So if I denote by L in MATLAB this exponential of some lambda exponential decay in length parameter times the length, then this L means this thing. This is this equation. This is this equation. So I tell MATLAB to solve for variables A and B, and MATLAB gives me the solution. So I have A and B as a function of the inlet and outlet temperatures. But okay, this lambda can be computed from the physical parameters. And now we'll discuss the meaning of mean temperature. We will define the mean temperature like this. Okay, later on, to avoid these bars, we will just skip that bar, okay? But first, we will consider that temperature is a profile depending on the position in the heat exchanger, so integrating the temperature and divided by the length is a very reasonable way of defining the mean temperature. Because this mean temperature times mass specific heat gives me total stored energy inside the heat exchanger. Indeed, the total energy will be the mass. This will be an infinitesimal volume element, cross-section times the infinitesimal length. This infinitesimal volume times density will be infinitesimal mass times specific heat times temperature. We'll get the stored energy in a slice of the pipe, and of course integrating that over all the length, we will get the total thermal energy of the fluid. Now we can realize that this constant S rho Ce can just exit the integral, and if I multiply and divide by L, nothing changes, but now I have here this average temperature, and this is volume times density is total mass, specific heat, average temperature. So indeed, this average temperature is the one we will need in our power energy per unit time balances. We'll get this derivative, so this will be the state variable in my models. Now, let us carry out this integral, knowing that the temperature profile inside here has this exponential formula. The integral of the exponential will be minus 1 over lambda times the exponential, and replacing the integration limits and dividing by L. I leave it for you. You know, the definite integral of an exponential is an easy exercise. This is the integral between 0 and L of this thing divided by L. So once I know this, I just need to replace this A by this thing and this B by that thing. So this piece of the formula will be just temperature difference divided by lambda L, and B will be copied without changes in here. So this is the average temperature as a function of inlet and outlet temperatures when I assume this internal distribution of the temperature along the pipe. As a remark, in this kind of pipes with no resistor, so we are, say, cooling a fluid, then in that case it can be proved from the partial differential equations that this is the formula for the temperature profile. So B is 0. Indeed, when I replace this by L, this is converted to 0. And this thing is the so-called logarithmic mean temperature difference. This thing, because the denominator, if you take logarithms in this formula, it's just lambda L. This logarithmic mean temperature difference plays a key role in many heat exchanger formulae, but our result is more general because we include the possibility of heating, and we are sort of extrapolating this thing to a transient, so this thing will move up and down based on the heating or the change of inlet temperature with exponentials in time. So we'll stick with this formula. If I place this to common denominator and I just write what multiplies the inlet temperature and what multiplies the outlet temperature, then we can prove, carrying out some operations, that the coefficient that multiplies the outlet temperature, this thing, if I call it beta, then the coefficient that multiplies the inlet temperature is 1 minus beta. So this is an important conceptual conclusion of this horrible stuff, is that the mean temperature is an interpolation of the inlet and outlet temperatures. If we carefully think, okay, it's kind of trivial. Yes, the mean temperature will be somewhere in the middle of the inlet and outlet. Not exactly in the middle, because that would be a linear profile, but indeed, if we plot beta, as this is a function of lambda L, then if I give values for lambda L from 10 to the minus 2 to 1000, 10 to the third power, I compute its exponential and I compute this formula. This is the plot I get when lambda L is small. Physically, it amounts to short length or low lambda insulated pipe. Then for short insulated pipes, we get that the mean temperature is half-half, which corresponds to a linear temperature profile. Indeed, if an exponential decay, I just cut it here, this thing will be very similar to a straight line. On the other end, if lambda L is very large, which means a long heat exchanger or a very conductive one, in such cases, temperature profile will be a fast decaying exponential or a slowly decaying, but okay, for a very long pipe. So in these cases, the average temperature will be very similar to the outside temperature because most of the length of the pipe temperature is very similar to the outside one. So in the limit, we'll have this kind of behavior. Of course, intermediate cases will have formulas like this one. Okay, the thing is that lambda can be determined from physical parameters, so beta can be determined from physical parameters for a particular heat exchanger in order to model the steady-state temperature distribution so that at least in steady state, our first order model matches the energy balances correctly. This is the idea of introducing this beta, with a clear interpretation between the linear profile in this extreme case and the approximation to the perfect stirring equations, mean temperature equal to outlet temperature in the other extreme. So now we have this expression of the average temperature. We had some bars here, but okay, to avoid filling with bars everything, we will understand now in our first order model T without inlet or outlet subscript as the mean temperature we were referring to earlier on with the bar. And beta is something that ranges between 0.5 and 1. But as this will be the state variable, then in our output equation, what we need to do is to solve for the outlet temperature. We know the state and the input, and the output equation will be solving for the outlet temperature. So I divide by beta, I move this to the other side, and I get this output equation. And then if I replace this output temperature in our power balance for our first order approximation of the heat exchanger, I can plug in that, and making some operations, we get this state equation. So with beta equal 1, it will be perfect stirring case. With beta equal 0.5, it will be linear profile, and we will get here at 2, 1 over 0.5. After dividing by this, so we get this state in these output equations for the heat exchanger with assumed exponential distribution of inside temperature and first order time dynamics. This would finish the modeling phase. Nevertheless, if I wish to compute the transfer function representation, either I set constant flow or I need to linearize this, transforming product of Ft to nominal flow times temperature in incremental units plus nominal temperature times flow in incremental units, we can linearize the state equation, and then this thing will be called mu to avoid clumsy notation, and taking Laplace transform. This will be the transfer function representation. We have 3 inputs here, so it's sort of transfer function matrix of the mean temperature And the outlet temperature, I need to replace T of S and subtract this. So with the trick of expressing 1 like this to put in common denominator and carrying out some operations, I get these 3 transfer functions for the heat input, for the flow input. This would be approximate because of the linearization, and for the inlet temperature input. Note here that as beta is less or equal than 1, 1 over beta will be greater or equal than 1, so this thing will be 0 or negative. So for beta different to 1, we will get a non-minimum phase expression of the model for the inlet temperature, which is reminiscent of the approximations of the transport delay, which is the true model. We'll see more on that on later videos in which we carry out numerical simulation of all this stuff and compare it to the exact partial differential equation solutions. So with this, we end. In this video, we have assumed that the steady-state exponential profile associated to the exact PDE solutions in equilibrium also holds during the transient of a tubular heat exchanger. With that, we have computed the mean temperature, and we have realized that it's an interpolation of the input and output temperatures, and the extreme case are the linear temperature profile or the everything approximately equal to the outlet temperature in the other extreme. Nevertheless, we can compute these coefficients based on physical parameters. With this mean temperature as state variable, we actually need to write the equation in this form, so this will be the output equation. We get this state space representation in state and output equation of our new heat exchanger, and linearizing the flow, if it's not constant, we can get these transfer functions for each of the inputs in our first order time dynamics heat exchanger, assuming some exponential profile to try to match the steady state so that the gain of this stuff is correct. I'm ending the video here. Thanks for watching.